Okay, the title of this talk is "What's our pattern for X?" So this is a question that I hear pretty frequently on projects that I work on and other projects. So like, for example, what's our pattern for doing form validation? I'm actually not going to talk about this question. We're going to circle back to it in a minute here. Um, Instead, I'm going to talk about guarantees. And specifically talk about adding guarantees to your application with invariants. Who here has heard this word invariant before? How it relates to software development. So a few people have. Those of you who haven't, an invariant is a condition or a rule that can be relied upon to be true during the execution of a program. This is just a really long way of saying an invariant is a logical guarantee about your application. So go through a couple examples. A type checker upholds invariants with regards to types and data of your functions. So really obvious and trivial example, if I declare a variable as a string, I can only use it as a string. And the moment I stop using it like a string, the type checker will stop me. So the type checker will give me an enforced guarantee at compile time that I'm using types in the way I said I would use it. To give another example, we could talk about immutability. So there are some libraries and languages that will guarantee invariance with regard to immutability. For example, there's a library called Seamless Immutable. This is a JavaScript library that allows you to create immutable objects. It exposes methods such that you can create a mutated copy of that object. But if you try to use JavaScript's mutation syntax to actually mutate that immutable thing, you'll get a runtime error. So this is a guarantee at runtime that your immutable things are immutable. And the second example is a language like Elm, where you can do the same thing, but in Elm, everything is immutable, so the syntax for mutation doesn't actually exist. So this is a compile time guarantee. In both cases, it's a guarantee, but they're one's at runtime and one's at compile time. So those are very close to the metal and low-level guarantees. We could talk about guarantees at a more abstract level. So we could talk about guarantees with regard to the application state. So application state invariants. To talk about one particular part of your application state, we could talk about asynchronous data. And we're familiar with these three with regard to asynchronous data. There's the success state, the error state, and the retrieving state. There's actually more to consider here. There's also the I haven't even made the request yet state. So this is the initial state. And there's arguably one more. There's arguably a zero state. This is a state where a response has come back successfully, but it came back with no data, but we don't want to show a blank view to the user. Instead, we want to either guide the user to some action on the page, or at least at a minimum explain why there's no data. So there's these 5 states that we care about with regard to asynchronicity. But on our projects, you might see something like this. You might have a customer data that has a few fields on it. So a customer's array, a couple of booleans that tell us whether we have fetched or we are fetching customers, and a string for an error. And the issue here is, even though we're using types and getting type guarantees, we're not getting any guarantees with regard to asynchronicity. All of our guarantees are implicit and unenforced, which really makes them not a guarantee anymore. This demotes them to pattern. This is just a way of doing things. Now, another developer may come along and they need to create some products type, right? And they look at this and they say, we're going to use this as inspiration for a products type, but this has fetched customers flag. That seems weird to me, because you could actually infer that we haven't fetched our customers or our products if either of those fields are null. So they say, okay, I'm going to infer we haven't fetched anything if products is null, so they do products a different way. Again, we have implicit and unenforced patterns, but now we have 2 ways of doing the same thing. Now the developer can come along and find a nit to pick and do their data some other way. And as we do on projects, sometimes we have developers that shift projects, and other developers join the project, and they're like, okay, what do we do here? I see 3 different ways for doing the same thing. Which pattern are we supposed to follow, and what's our pattern for structuring asynchronous data? These questions are completely reasonable given the way we currently do product development. And I would assert that rather than asking what's our pattern in hindsight, we could proactively ask what guarantees can we add to our applications. So we can get async state invariance by carefully modeling our data, by spending a little bit more time, an hour, another 2 hours, thinking about how to model our data. So here's one way to do that. This is called a union type. So this type allows me to enumerate 5 different values, and these values map one-to-one to the 5 asynchronous states that I care about. And the success and failure state are parameterized, but they contain a payload. So this will be the data that we care about. So now the question is, I have customer data. I know it's asynchronous. How do I model this data? Well, I use my remote data type. The A on the remote data is my list of customers because that's what comes back with the success response. The B, which is the type of the payload for the failure, is an HTTP error. And now everything just kind of falls into place and becomes unambiguous. What is the initial state for my customer data? Well, of those 5 options right there, only one makes sense, initial. If I navigate to a page and I want to go fetch some customers, what state makes sense to assign to my customer data? Retrieving. Like, so this all becomes very obvious. If we look at our view function, we could define a view function that accepts the customer data, returns virtual DOM, and we could just pop open that union type and say, okay, which one are we, and show the appropriate view. And what's more is the compiler will force us to handle all 5 of these states. So now what we've done is we have a compile time guarantee that if we're showing these asynchronous data to the user, we have to handle these 5 situations. Otherwise, the program will not compile. So this is a guarantee that we want. And to go over another example, we can talk about other invariants with regard to user experience. So some of you might recognize this. I took this from one of our AngularJS projects, ported it to Elm, and we could talk about different ways or different invariants with regard to a tab panel. So this is what this is. This is a tab panel. For the sake of time, I'm only going to talk about 2. So one of the invariants, one of the rules that we want is these tabs should act like a radio button. Only one should ever be active at a time. So that's rule number 1. Rule number 2 is, in talking with our designers, they say we want a bottom border on the active tab. But depending on where we put it on the page, we also want to be able to configure it to have a top border. So we have this either or situation where we want a bottom or a top border. So these are 2 rules we want to have enforced. But if we look at how we model this, we have this tab view panel that has a display text and an isActive Boolean flag. So every tab has this model. But we have a problem here because this isActive flag is on all of the tabs. And what this means is we have to manually sync up all of these Booleans to make sure that only one is ever active at once. So rather than guaranteeing us that only one is active, this is essentially guaranteeing that we will one day have a bug where those flags get out of sync. It's not the kind of guarantee that we want there. Looking at the view function, if you take an AngularJS component binding and port it to Elm, this becomes a view function with a laundry list of arguments, and it returns virtual DOM. So there's a tab click handler, a couple of Booleans for determining what border is highlighted, and a list of tabs, which we show above. Again, a couple issues here. In addition to seeing true, false, and false, true just kind of out in the open, that's just being hard to read. These 2 Boolean values represent the same thing. They represent which border is highlighted, but they can also get out of sync. False, false is not valid, and true, true is not invalid. So again, we're modeling our data incorrectly and essentially guaranteeing that one day in the future, it may not be soon, but it may be a long time from now, these will get out of sync, and that'll be a bug that we're gonna have to fix. So spend 30 minutes refactoring this, and this is what I came up with. Our tab view model still has display text. I took out the isActive flag because we don't want to have to synchronize that, but I threw in the onClick handler as a personal preference. I like co-locating my click handlers with the actual thing I'm clicking. There's this tab panel overarching view model down right here, which the way I've modeled it lets me get other invariants that I'm not going to talk about, but the thing to look at here is there's an integer that represents the index of the tab in our list of tabs that is active. So what this essentially gives us is at compile time, this guarantees that there will be at most 1 active tab because there is exactly 1 integer there. You can't have more than 1 because there's only 1 index to keep track of. So that's another guarantee that we can get. We can then write more code later on that checks the value at runtime to guarantee that it's a valid index. And that will guarantee us that there's exactly 1 active tab. So this is just ways of adding guarantees at runtime and compile time. And then lastly, the 2 unreadable bools that I talk about, they become a union type. So this is more readable. More importantly, this adds a guarantee that only one of those borders will ever be selected. You can't have both, and you can't have neither. So these are more compile time guarantees that we can get. And as a nice side effect, our tab view function cleans up a little bit because it's in the format of give me a view model and give me a config. I'm going to invoke my tab view. So give me the tab panel view data and give me the configuration. Give me whether the top border is highlighted or the bottom border is highlighted, which reads very naturally rather than seeing a laundry list of arguments. So I'd assert that instead of asking this question, what's our pattern for form validation or enforcing every form has autofill set to off? Or what's our pattern for doing a wizard? We want our user experience around a workflow wizard to be same here as it is here, right? We want these kinds of guarantees. I'd assert that rather than asking what's our pattern in hindsight, we could be proactive and ask, when we first build these features, how do we add guarantees? How do we guarantee that certain bugs are unrepresentable, and how do we guarantee certain user experiences with regard to these features? And so in summary, I think there's two ways to get to that point. Number one, you can get app guarantees by using the right tool for the job. If you want runtime guarantees, you have to choose the right libraries and the right frameworks, in addition to being exhaustively disciplined. Okay, so runtime guarantees require you to put in extra effort to make sure you actually get these runtime guarantees. If you want compile time guarantees for low-level concepts like types and high-level concepts like user experience, then you need a type checker. That's the only way you can get compile time guarantees for those abstract concepts. And then lastly, I think it's also a change in mindset from building features quickly to building features deliberately, because ultimately I think building features quickly is only quick in the short term until inconsistency and bugs slows you down in the long term. Whereas if you are deliberate with modeling your data, you're deliberate with ensuring a consistent user experience across your components and your data, that's faster in the long term. Even if it's a little longer in the short term, it's faster in the long term. Or at least in my opinion, I think that'd be the case. So I'm curious if this provokes any comments or criticisms or good ideas or bad ideas. So yeah, Evan, what do you have?
I think the biggest question is, how do you deal with being unable to guarantee guarantees, right? Because our business partners can always change how a wizard works. So we can't write code off of a guarantee and then ensure that that will match with the user.
Yeah, so the guarantee is sort of self-documented in some sense and sort of inferred, that's right. But however, if it's a compile time guarantee, that's the way it is in the application. And if they change, let's say the tab panel can have only 2 active tabs instead of just 1. Well, now we can change our code, and the compiler will tell us everywhere else where that guarantee is now a mismatch, and the program won't work until we go fix everything. So yeah, you can't guarantee your guarantees, but I think it's still a step up from where we are in some of our projects where it's untyped and we just don't know when things break. We don't know until the users tell us or QA tells us.
It's just hard to enforce. Because Elm, for instance, the language itself lends itself to these guarantees. But how many Elm developers do you know? And then you start tracking it and go, okay, so our business partners chose Angular and JavaScript, not TypeScript.
So this isn't something that's just for Elm. I mean, TypeScript, you can get this with TypeScript. TypeScript has union types. It's has type inference, and has a compiler, obviously, so you can get compile time guarantees. So the syntax is just heavier with TypeScript, which is why I demoed it not in TypeScript, but it works with that.
Right, and I was just saying that sometimes our tool set, based on client needs, it can't match that.
And this is why I brought up this slide.
Right.
Because we don't do this. We don't use the right tools for the job. Or not very often, I don't think. So yes, it does require a lot of pushback for the tools that we're using. Okay, sounds like there's no other feedback. If you want to come talk about it sometime, come find me. I'd love to talk about it. Otherwise, that's all we had. So thank you.